previous episode was theory, where we understood what exactly is optimization, what exactly is our tree parser estimator algorithm, and a whole lot of theory about how everything comes together to build an optimal design. How exactly do we figure out what is our global maximum, and how does the algorithm smartly understand which design to test next? This episode is where all of it comes together to life. We are going to configure an Optuna study, wire it to our OpenFOAM automation loop, and let it run at least 20 rounds of Bayesian optimized CFD. And by the end of this episode, we'll have an optimal heatsink design that's about 87% more thermally efficient than the baseline. So the code is live and the data is real. Let's go. Series checkpoint. Episode 2 was the baseline. Episode 3, we did the parametric sweeps. And episode 4 was the algorithm theory. Now, episode 5, we do the live run. Episode 6 will validate the optimal design in a conjugate heat transfer simulation with a more realistic boundary condition. Episode 7 will be the full code walkthrough. Everything, all the code, the driver, the template case, the results is at cfd-openfoam/youtube-series on GitHub. The driver has 4 building blocks. First, the study, second, the objective function, third, the pruner, and fourth, the sampler. They snap together in one line, study.optimize in objective and end trials 20. The study is the container. It holds every trial that's ever run, and it passes to an SQLite database on disk. That single flag, load if exists equals true, means if the progress gets killed at trial 12, you restart it and it picks up at trial 13. No reruns, no lost data. Direction, maximize. We're looking for the highest Q over V. Study name matches what's in the database, so reruns reconnect. The TPE sampler with seed 42 gives us reproducible trial suggestions. The objective function wraps one complete CFD evaluation. Optuna calls it once per trial. It gets past a trial object and it returns a float, Q over V. The algorithm tries to maximize that float over every trial. 3 suggest calls, one float for fin thickness, one integer for fin count, and one float for fin height. Those 6 arguments, the bounds, define the search space entirely. Everything else is fixed. Then is manufacturable. This is the pruner. It checks 2 things precisely. The fin spacing must stay above a minimum, and the aspect ratio, this is height over thickness, must stay below 25. If either condition fails, we raise trial pruned. Optuna skips the CFD call entirely. No 8-minute wait, no resource waste. The trial is logged as pruned, and the next one starts immediately. If the geometry is valid, we call run_single. That function runs the full pipeline of block mesh, snappy X mesh, void simple foam, and post-processing to extract wall heat flux. It returns Q in watts and V in cubic centimeters. We divide and return. One more thing before we start the live run. We already have 15 sweep runs from episode 3 sitting in results.csv. Throwing that data away would be wasteful. The TPE model works better with more history, even from non-BO runs. So we seed the study. Before the first Optuna trial runs, every OK row from results.csv gets loaded as a precompiled trial via study.add_trial. The TPE model now starts with 15 data points already fitted. It immediately knows that thin fins are good, that many fins are better, and that height has diminishing returns. That's a massive head start. The seed block loads the CSV, filters for OK rows, creates optuna.trial.create_trial objects with the correct distributions, and it adds them. Duplicate parameter sets are silently skipped. The seeded study has about 15 preloaded trials before it starts. The first thing you want to do is check that you are actually in the right environment. This is Heatsink OPT. Now the command is the Python optimize heatsink and optimize. There are some helpful arguments if you want to take care of that. There are 5 different arguments that you can see here. Now of course the first time I ran it into a very good error here. The issue was that the working directory was not properly placed. Now that we have a flag for that, I'm essentially exporting the working directory for the results using this particular command. You can find this in our GitHub repo. And now that I have the check flag, I can see that everything is verified. I have the all checks passed, ready to run, and now I'll just run the script with optimize flag. Let's do 20 trials. And there we have it. The first few trials cluster around the thin fin region immediately because the seeded history already points there. You'll see trial numbers, the parameter suggestions, and the Q over V results after each 8-minute CFD run. Some trials do come back with STL failed. This is the pruner at work. When the fin spacing is too tight, 11 fins at 1 mm each on 60 mm base with certain combinations. The geometry generator tries to create fins with 0 or negative spacing. The STL is going to be invalid and trial will be logged as failed before even the CFD starts. Using this strategy, we saved about 80 minutes of CFD calls. Around trial 18 in our study, the algorithm locks onto the thin fin regime and stops exploring. It's found Q over V above 2.1 and it starts exploiting the region around n equals 11 and t equals 1 mm. That's the algorithm doing exactly what it's designed to do. Let's look at the convergence curve. Each dot is one CFD run from phase 2, plotted by run number on the x-axis and Q over V on the y-axis. The red line is the running best. The grey dashed line is the baseline, 1.08 watts per cubic centimeter. The very first Bayesian optimization run 18, lands at 2.133, already double the baseline. That's because the seeded history pointed the TPE directly to thin fins. By run 21, we are at 2.22 watts per cubic centimeter. That's the highest raw Q over V in the entire study. The parameters are n equals 11, t equals 1.01 millimeters, and h equals 23.7 millimeters. The algorithm has essentially converged by run 20. The remaining runs explore slightly different combinations of the thin fin region, confirming that the plateau is real. The validated result is run 47, an independent rerun of the same optimal design, which comes out at 2.019 watts per cubic centimeter. That's the number we trust. The contour plot shows n on the x-axis, h on the y-axis, and Q over V as color. The hot region, the yellow peak, is at n equals 11 and h in the range 20 to 25 millimeters. The coolest region is at low n and the extremes of h. Notice that the peak is not at the tallest fins. H equals 24 is better than h equals 30. Beyond a certain height, adding more metals gives diminishing heat transfer and growing volume. That's the Q over V objective naturally balancing performance against material. Also notice the color is almost uniform across H for any fixed high N. Height barely matters. That's the fan-over result already showing itself in the contour. The gradient in the N direction is steep. The gradient in the H direction is nearly flat. Fan-over stands for functional analysis of variance. It decomposes the variance in Q over V across all the trials and asks how much of that variance is attributable to each parameter. Optuna computes it automatically after the study. The result, fin thickness accounts for 67% of the variance. Fin count is 25%, fin height is 8%, the T dominates. The practical implication is enormous. If you're a designer with budget for one manufacturing improvement, invest it in tighter fin tolerances, not taller fins. Going from 2mm fins to 1mm fins nearly doubles Q over V at fixed count. However, going from 25mm fins to 35mm fins barely moves the needle. This is the result that's hard to find by intuition. Individual sweeps from episode 3 showed the T trend, but they couldn't show that T matters 8 times more than H. That's what the joint optimization, the fan-over decomposition, and the full experimental design gives you. Here's the final result. 11 fins, 1.01mm thick, 23.7mm tall, volume 26.6 cubic centimeters, that's 17% less material than the baseline. Q over V of 2.019 watt per cubic centimeters, that's 87% better than the baseline of 1.08. Absolute heat dissipation 53.7 watts versus 24.6 for the baseline. Thermal resistance of 0.93 Kelvin per watt, down from 2.03. That's a 45% reduction in thermal resistance with 17% less material. In episode 6, we take this optimal design and run it through conjugate heat transfer simulation. So one of the biggest mistakes, or rather the assumption that we took here, is a fixed wall temperature, actual aluminum conductivity, the heat generation in the base, and a more realistic thermal boundary condition is what's really required for you to truly understand what's happening with your heatsink. That's what we'll do in episode 6. We want to see whether the gain holds when the simulation gets a bit more honest. If you've been following along, you've built the baseline, you've ran the sweeps, and now you've understood the algorithm as well. You just need to now run the optimization loop itself. The optimal design is already live on GitHub. It's in the day 5. And subscribe if you want to see how it performs in episode 6. Code is on the GitHub, link is in the description, and I'll see you in the next one. Keep your residuals low.